Okay, I think we can get started. So as you can see, in my traces folder, I have a training folder where I have all these packet traces that I save up for the year, squirrel them away, so I can either do in-house training or bring them to SharkFest. So in City, what I do is once or twice a quarter, we hold in-house training. And it's pretty in-depth in that we take a look at one trace file for about an hour and a half or so. Right? So we dedicate about that much time, same amount of time as here, but for one trace. And we kind of deep dive into every single packet interaction, etc. So my plan is, because I've been getting this request from internally, is to record those and then put them up online. So if I do that, then I'll let Janice know so that you guys, who attended, will get an email saying it's posted here for download, etc. Intra training, obviously I don't have to anonymize any packets, so it's a little bit more work. But anyway, so keep an eye out for that. Okay, so today's session is same as yesterday's session. Is anybody here who didn't attend yesterday's session by any chance? That's about 25%. Okay, so it's same, but yesterday's session was more about philosophy, right? Kind of like, and we're going to touch on that today too, but we're going to go a little bit more into packet level troubleshooting. I'm going to go through the first two pretty quickly. In fact, I may even blow through them, and because the later traces are more interesting, right? So the beginning ones are basic, but kind of good building blocks, so we'll kind of jump right to it. So this is an MQ slowness. And again, problem gets escalated. You see the problem statement. MQ transfer stinks. The network's having an issue. Please help us fix the network. And my stock answer is, well, it will help you fix your application. And so, again, throughput issue. First things you should rule out are duplex. Absolutely. First thing I ask, duplex that right? What else? Window sizes. Okay, and what else? Latency. Long fat network. Exactly. I am fat, but long fat network. That's exactly right. So if you don't know what long fat network means, just Google for RFC 1323. Okay, and you'll see what long fat network and why it presents a challenge in modern day network. So let's take a look. So here's the actual MQ transfer, and we'll take a quick look at the window size, 65K. Not too bad, right? Could be better with scaling, but as a start, not too bad. Does it have any option field next to it? No, which means that there's no scaling going on. What about the other side? 64, okay. Little odd number there, 64860. But again, nothing to complain about. So if we look at this trace, when you first eyeball this trace, what should you do? For those of you that attended yesterday's session. Anything show up? No, nothing, right? And so it looks pretty clean. How about the evil odd packet that we talked about yesterday? Do we have data, act? Looks okay, right? So if you are eyeballing this traffic, is there anything that comes to, again, pattern recognition is the key to protocol analysis. So what do you see on this screen that warrants some yeah, so both of them. The delta immediately jumps out, right? Very consistent. And what happens just before the delta? The push. And what does that typically signify? Application level flow control. What this means is that the application here, that's sending 1380, right? Sending 1380, and then it sends 1356. So let's take a look, right? 1380 two times, and then, what was it, 1356? 4116, 4K, about 4K, right? When you see numbers like 4K, 16K, 32K, 64K, those are boundary numbers. You need to pay attention to them because because they don't happen just for a reason, right? So keep a mental count of these numbers that you see in computer science, okay? And they're typically 2 to the 16 numbers, right? Or power of 2. So, but when you first look at this, it looks okay. So let's represent this in a different way. And one of my favorite tools to use is Stevens graph, and it doesn't work here because let's see here why Stevens graph is not working. Okay. All right, let me come down here. I chop these packets up, so sometimes I have to finesse it into working. All right. So Stevens graph. Well, let's take a look at the Stevens graph. This line here looks very similar to the keynote presentation, right? Not that I'm even close to where Matt Jacobson was, but it's the same problem. All this is time and the number of bytes transmitted. And the number of bytes transmitted is represented how in a packet trace? Sequence number. So sequence number is nothing more than the number of bytes being transferred. There's nothing magical about it, no mystery. It's just 100 bytes, 200 bytes of transfer. Okay? So should this line be the slope here? Should it be lower or higher? Ideally. Ideally higher, right? So that if it takes off like this, that means you're putting more through, or you're getting more throughput over a shorter amount of time. Okay? So when you first look at this, you're thinking, yeah, this looks okay, right? So let's zoom in. And you just left click. And then you start to see, right? What do you see here? At this time instance, what do you see? These little dots are packets, right? So let's go back over to our main screen, and it happens to be this packet, and the smaller packet, okay? And so right away, you say, all right, what's the time interval here? About a second. 4K every second, the throughput is 4 kilobytes per second. And they reported they're getting about 4K throughput per second, right? So is this the network's problem? No, absolutely not, right? If it was the network at fault, what should you see in the trace file? Retransmissions, right? That's the TCP's way of throttling down, okay? So TCP's way of dealing with, hey, I'm too much congestion here, whatever, is it starts to lose packets. TCP goes down, does a slow start, right? Different stacks will react differently, depending on whether it's Reno, Trino, etc. It'll either go back down to 0, start up, or it'll say, I've been down to 0 before. Do I really need to slow start all the way from 0? Let me just go halfway and see how it behaves. Okay, so these are some of the tweaks in the newer stacks. And this is why newer stacks from Microsoft and Apple behave better than older stacks like Windows 2000. Okay? They handle failures a little bit better. Yes?
What would happen if the packet really encountered congestion, so it wasn't being dropped and really held in a queue?
So, okay, so that's actually a great question. And, and it's actually a problem of, is buffering good or bad, right? So the answer is, again, it depends. Because when you buffer too much, you fake TCP into thinking there's adequate bandwidth, right? TCP can deal with packet loss, but if retransmission timers and delayed act timers are not going off, TCP doesn't know how to behave, right? So sometimes it's better to drop than to buffer. And this is exactly what happens when you set up QoS on Cisco routers or any type of routers. It starts to tail drop, and it depends on how it tail drops, right? The dumb way to do it is take the last 100 bytes and just drop it, right? But if it happens to be the same FTP transfer, you're totally screwed. A better way to do it is flow-based. You say, all right, I'm going to drop a little bit here, a little bit of this traffic, a little bit of this traffic, and, oh, by the way, I'm not going to wait till I have congestion. When I see, I'm the router, when I see that I'm about to hit a threshold, I'm going to proactively start dropping packets on different flows to throttle people down. Okay, this is like when you go on a highway and you have green light, red light for every other car to hit the on-ramp, right? It's better to gate people so that you have a smooth flow of data than just have everybody do a mad rush to the highway, okay? So buffering is good so long as you don't buffer for too long and TCP gets confused, okay? Because you're not solving anything there, right? TCP is going to continue to ramp up, you're going to have to continue to buffer, and eventually you come to a crash condition. Okay, so this one is pretty simple, right? Sequence number, so I'm going to kind And when I post these presentations, by the way, I'll have the answers and detailed reasoning behind all these questions that I ask, right? Look for patterns. We looked at the push bit, right? So from now on, you're going to be tuned into that push bit and what it means when you do analysis, okay? Okay, graphing tool. Okay, good. So next question. So I'm not going to go through this. Basically, this is a receive. I have a receive side and server side, send side trace, and it's Snoop actually dropping packets. Okay, so it looks like a retransmission packet loss condition, but it's not. Okay, and the one thing here that I put is Occam's razor, and basically what this means is in any engineering problem, really, or any problem, the simplest answer is probably the correct answer, right? So don't go looking for esoteric bugs. Don't go looking for, off the beaten path. Look for the most usual suspects first. Rule those out, okay? Very rarely will you find odd problem. I mean, I find them for some reason, but it's great for me because I bring them to SharkFest. Okay, yeah. So here's a good one, and this actually, someone during Loris's presentation asked about the duration of TCP, right? Can you write a script to keep a duration of TCP packet socket? And I said, yeah, you know what? You can do that with the summary tab. So here's a problem description. City developers are writing an application to work with an internet-hosted vendor, right? They're doing all the intra testing, and everything's great. And they're getting ready to go live, and they said, all right, let's start testing with a vendor. So they do. Throughput stinks. So when I got this problem, I did what I shouldn't do, is I blamed somebody. And I said, you know what? Most likely, if it works within the city's network, but not when you go to an outside vendor, there's really two problems. What are they? Who's really at fault, most likely? The developer's always at fault. No, I'm just kidding. I'm just kidding. First, who do you talk to when you talk to the internet in most corporate networks? ISP, but even before ISP. Firewall or proxies, right? Very few companies allow you to talk to the internet directly, right? So, and the other one is obviously internet, and you can't troubleshoot the internet, so you just kind of say, hey, lost cause there. But I said, go talk to the proxy guys. They should be able to help you, because if it works great here, but it doesn't work when you go to the internet, and there was no packet loss, and I just checked that there was no packet loss, then most likely it's a proxy issue, right? They went to the proxy issue guys, a week or two, comes back, says, no, they didn't find anything, something's wrong. So I said, all right, we took the trace, and we had what I call high bandwidth conversation. So I got my team together, and I picked 3 or 4 guys, and I said, let's look at this trace, because something is not working, and I don't know what it is yet. So we need to sit in a room and figure this out, right? And this point here, this is my little Hansang Bayism, is defaults are the guardian angels for the clueless. What I mean by that is, in every appliance, every product, they dumb it down so that help desk won't get a phone call, right? And it doesn't mean that you should tune it up to be on the, 3 standard deviation away from the normal. I'm not saying that, right? But for the most part, defaults are safe values and things that may or may not be of interest to people who are trying to solve problems, okay? What do I mean by that? Let's take a look. So, yes.
When your developers are tested internal with use of the internet, do they ever use any kind of WAN emulation?
Yeah, we do. So 3 ways to do that. One is I'm building a lab for them now where I use VMs with the appliance, where I'm going to give them an address space with the network characteristics since I own the network.
What appliance?
Right. We're using a NUI. Okay. Right. So a NUI, I can say, put your VM in a 10 dot address space, talk to the 192 address space, that's Singapore to US. Go to 20 dot to 172 dot, that's EMEA. Right? And I know the network characteristics because the network belongs to me, so we're going to do that for them. The other way we do it is we get a packet trace and we use IT Guru from OpNet to do simulation studies. Okay. And IT Guru from OpNet, and that works well, so long as you take care of the garbage in, garbage out. Okay. OpNet reports look very official, very technical, and you can be fooled into saying, oh, this is my answer, and it's not. It's just the input was garbage, so the output is garbage. So again, let's take a look at some of our key things that we do. Okay, Windows Update, what does it mean?
The window just increased.
Yeah, right? It means that this 10.guy said, hey, I was kind of congested a little bit, but now my window size is opening up. So yeah, I can send more data, or send me more data. Okay, is that a problem? Are you like concerned when you see this trace and it's again 13 out of 2,800?
Looks like it happens about 3 times.
So you need to look around here, right? These are like searchlights telling you, and they happen in bunches, I guess, which is actually kind of normal. But I wouldn't be too concerned about them, so long as, because I don't have a 0 Windows event that happens before the Windows update, right? If you see a 0 window just before the window update, that means I've exhausted all my resources as a server. I need you to stop talking. 0 windows are a very bad thing. Okay, that means no more communication can happen. And then Windows Update will say, okay, now I can talk to you. But unless it's a 0 window event, the fact that the window size went down and came back up, not really a problem. It just means you're using your server efficiently in a way. Okay, so let's take a look. So we're looking at this. Nothing really jumps out. So they seem to have some MTU and block size manipulation. I know that because I see kind of a pattern of full size, small size, right? Deltas look okay, right? And another cool way to do that is you sort on delta, see if you see any familiar numbers, right? Like 100 millisecond consistently showing up. Not really, not in this case. So what else could be wrong?
I see a lot of fins.
Perfect. So someone already recognized when I was scrolling down that there was a lot of fins, right? So if there's a lot of fins, there must be a lot of, not necessarily retransmission, connection opening. So we have 100 connection opening out of 2,800. Good or bad? I don't know. But when I see a lot of connection opening up in a short amount of time, right? Look at the time here involved. Then I get a little bit concerned. Because what's the penalty of opening up a new TCP connection? Handshake and slow start. Okay? I'm going to waste round-trip times to set up the TCP connection. Then I can't send you a full-size packet right away. I have to slow start. Okay? And a lot of people kind of poo-poo the slow start, like, who cares? But here's a concrete example. Let's say you have, do the math here, easy, 100K of data to send. No, forget that. 10,000 bytes to send. Okay? You have 10,000 bytes of application data to send. And your MSS is 1,000. Okay? How does slow start transfer that packet?
It sends one segment first.
One segment first.
Until the ACK is received, then it
goes to 2, 4, 6, etc., right? Now, what if that round-trip time is 300 milliseconds? You have to wait 300 milliseconds before you get the first ACK. Then you have to send 2, wait for the ACK. You just wasted 600 milliseconds. By the third slow start iteration, you wasted 1 second. Okay? As opposed to, if I didn't have slow start, I could have sent the entire 10,000 bytes in one packet train. Meaning, send, because I have enough adequate send window. And I'm done in one round trip. So instead of finishing in 300 milliseconds, I'm going to now spend 1.5 seconds transferring that same amount of data because of slow start. Okay? So, perfect recognition here. You looked at the SYN. So as soon as we saw that, we said, now this is kind of weird. Should we look at this? We did. Of course, otherwise I wouldn't be here. And we said, let's take a look at conversation list. And let's look at TCP. And this conversation list is presenting you the same, these are socket numbers that open up. They open up and talking to the internet through 8080. And the number of bytes here, we questioned it. But they said, oh, it's the same test data that we're sending over and over. I said, all right, no problem. Bytes. Everything looks okay. Then we kind of had an epiphany. What else affects TCP performance? And we said number of TCP connections, slow start, are we hitting slow start? So we kind of went off in the deep end there a little bit. And we said, yeah, there is some slow start penalty, but not terrible, right? Then we did this. Relative start. And we were looking at them, and as we were having this high bandwidth conversation, someone noticed a pattern, right? And unless you do this day in and day out, it's hard to pick out this pattern, right? So we said, we don't want to look at it in here. Let's use Excel. And did I put that? Did I embed that? No, I didn't embed it, of course. Let me. Where would you want it here? Advanced.
I use Pilot too. How much do you use Pilot up front?
This was a pre-pilot.
Okay.
This was from last year. Yeah. So what graph do I have here? Okay, so let's zoom in a little bit. Let's make it 200%. What is this? These are socket numbers over time. Socket first, 2, 3, 4, 5, 6, 7, 8, 9, 10. Interesting. When do these start? Not so much seconds, but when these four stop, these four kick off. When does this one kick off? About here, right? And then, and so as you move up and down this chart, let me zoom out a little bit. What we saw was that this application was limited to 10 sockets. Okay, there was an upper bound on the number of sockets the application, which is actually a pretty good thing. You don't want to have an application that runs away with sockets. Okay, but here there was enough bandwidth to handle additional sockets. The server had plenty of memory, but once the first 10 went out, they couldn't do anything until the first 4 finished. And then the next obvious question is, we saw the data size cargo, right? The data size that was being transferred was about 18K, if I remember right. They were all the same, were they not? So why does this take longer to finish than these guys? If I go back to the trace, and I look at the conversation, okay? And again, this is what separates a real packet analysis guy from someone who's just doing this part-time. We said the number of bytes is about the same. Sure enough, 18K. Right? We proved it. Then we looked at the chart, and the start and stop time is a little bit different. Why? We have adequate bandwidth. If we lost packets here, we would have seen retransmissions, and we don't. Multitasking. Multipath. Possible, but not likely. So again, we're doing the zebra. But multipath is a possibility, especially if you have a bonded interface. And actually, I did ask that. Are we using multi-link PPP with per packet load balancing? The answer is no. The answer is simple. Don't overthink the problems. The first 4 happens quicker than the next set of 6. Why? Server's busy. The server can process these 4 quickly, but the next 4 have to go into some kind of a queue. So this is server think time that's responsible for this. Otherwise, if they all started and stopped about the same time, it should actually kind of start a little bit slanted, right? Because these packets don't leave out of 10 separate NICs. There is some serialization going on as packets leave, but not this much, right? And it turns out that when we talk to the vendor, oh, by the way, you might want to tweak your CPU or how you handle it, because the first 4 are handled exactly right, and then the next ones are not. So they had a hard limit of 4, right? They gave preferential treatment, and then they kind of slowed down. So not only did we find a problem with number of TCP connections, but by looking at it in a slightly different way, we were able to quickly see, oh, this is very obvious, right? Who can't figure that out, right? These 4, these 4, these, picture's worth 1,000 words. But the problem is that, once again, getting to this stage is the hard part, right? If someone shows you this, it's easy. But how do you get to that stage? Practice, right? And again, picking up patterns, okay?
Where did you do the trace from? On the box? Or
We did it on a closed site near the proxy, actually, because initially we were suspecting the proxy. Okay, but we can actually figure that out too. We can figure out where we do the capture by looking at the packet traces. Okay, any questions so far? Yes.
Was the server on the far side your server? Because you said it was a client. Was it?
We're the client.
Okay, so it's not on your network. I
Yeah.
guess in other words, like we run SCOM, so if it was a CPU.
Yeah, so what we told the vendor was, look, we're about to jack up our number of sockets from 10 to 100, right? Because we have an SLA to meet with these records. So if I already saw that after the first 4, you choke, your server chokes. We're going to send you 100. What's going to happen to your server? And they said, well, let's work together and figure it out. Right? So they got their developer on the line, our developer on the line, and we settled at 100 sockets at a time. And 100 sockets was enough to keep the bandwidth somewhat full without the servers dying. Okay? And they went from minutes to seconds. Yes?
So why did the application vendor say why they were opening so many connections?
Okay, so that's actually a good thing to do. You should always have upper bound on your programs, right? Because you don't want to just have a runaway process going nuts. In this case, it's default. Again, so the application environment they were developing in defaults to 10 sockets if you don't specify it.
So what kind of app was it? Was it? It wasn't file transfer, obviously, right? This was some kind of interactive app.
This was actually a customer data crunching for marketing opportunity. So I actually help people call your homes to say, would you like to, I know that you're using a credit card, would you like to buy some savings again? So that's what it was doing, okay? So don't blame me when so they can have more phone calls. Now this one is absolutely fascinating. This one took me a little while to figure out. Even though I knew what the problem was, I didn't know how to fix it. So this is actually the same system that we looked at Tuesday, where they get the patches ready for 300,000 users, and these are staging servers. And again, it sounds like they have a lot of problems, but this is over a course of the year, right? I'm not picking on that group. So again, these staging servers need to get these packages, Office, patches, and all these vulnerability, McAfee updates, all to different staging servers that people can get to the closest server and download them. But that transfer was slow, right? So immediately we'll look out, again, I know I sound like a broken record, but if you do this, 70% of your throughput problems will be solved if you just do these 4 things. Okay, trust me, I do it every day. And if you check the duplex, window size, packet loss, and not even packet loss so much, LFN, long fat network, you're going to rule out 70% of your problems. And in fact, they're so easy to figure out that you can give it to a junior person and just give them a set of guidelines, window size, etc. Okay? So we're going to look at the information. It says not all inefficiencies come into play. Does Windows size come into play here? So let's take a look. So right after I said do these 4 things, I'm going to tell you, don't worry about it. Why? Why should you not waste your time looking at TCP window sizes here? Why?
Because the round delta time is so low.
Deltas are not good, more accurately, very small. So this is a LAN environment. When you have a LAN environment, throw Windows problems out. Okay? Window sizes rarely come into play when you have a LAN environment. Okay? Because I can go from here to there very quickly and back. Okay? So even if I have to move a mountain of sugar with a teaspoon, if I do that really fast and I don't have to go very far, I can do that. Okay? So what else?
There's a duplicate act on the three-way handshake.
So there's a duplicate act here. Yeah. Yeah. So let's take a look and do our thing. Right? Broken record. One dupac. Is that a big problem? 11,000 packets, one dupac. Should you go nuts? No. So again, throw that out. Okay?
How many pushes?
So, perfect. So let's start looking at it. Do we have a lot of pushes here?
Yeah.
We have some. Right? Here's one push right here. right? So I'm going to scroll down and try to kind of keep up. And every page has at least one push, right? So it's actually very easy to either do Stevens graph to see how many dots line up in a vertical row, or you can count them manually. Okay? Is it a problem here? The fact that it's pushing every page length or so?
There's no high deltas right up there.
So how do we check? Well, let's use the Wireshark tools. Let's set this as a time reference. Okay? So this is a push that happens. And before we do that, let's look at the acknowledgement number. Sorry. 493 is what the ACK number ends in. And this guy says next sequence number is 493. So what is it saying? This guy is saying, I just sent you 260 bytes of data. When I talk to you again next time, I'm going to start from here. Okay? So this is the sender. The receiver is going to say, hey, I've got up to this much. I'm all caught up. We're good to go. And when we look at the ACK number, that's exactly what that says. ACK number 493. We're all caught up. There are no packets outstanding. Okay? There's no bandwidth congestion. There's nothing. Everybody's all caught up. And then about 400 microseconds later, it starts transmitting again. Okay? So let's see how much data is being sent by the application through what we call buffer tearing, right? So we're going to mark this packet, and then we're going to look for our next push. And it happens right here. So let's scroll over to our cumulative bytes. And what's the number there? How many bytes are we sending per application buffer? About 17K. Is that a boundary number? Yeah, sort of is. 16, 17K, right? So here's the difference. Network people count in 1,000, a kilobit is a kilobit. Server guys will say kilobyte is 1024 bytes. Okay? It's the old computer science issue. But the network guys are always right. So a kilobit is 1,000 bits per second. So 17K happens to be a boundary number. Again, you should kind of, it's a typical socket sizing number. 17K in a LAN environment, do I need to worry about that? Not really. Do we have the evil odd packet problem here? So let's go back and look. 1, 2, 3. Next sequence number, 133. My acknowledgement number, 133. All caught up. Okay? So we're looking for any delays that might be caused by odd number of packets. So far, everything looks good. But here's one, right? So let's start from here. Next sequence number, 913. And the acknowledgement number is 913. I'm all caught up. I send 1, 2, 3 packets. So right here, you kind of say to yourself, odd number of packets. Typically, not very good. But look at the sequence number here. Next sequence number is 093, ACK number 093. I immediately ACKed it. That's a little odd, isn't it? RFC says to do what? How many should you ACK? Every other packet. So theoretically, when the first 2 comes, you should send out an ACK. Right? 2 packet comes in, 1 ACK comes back. 2 packets go out, an ACK comes back. That's how you're supposed to play. But here we see 1, 2, 3, and then an ACK. Why is that? Again, you need to kick it up a notch and figure these things out. Why?
Maybe you're not seeing the other ACK from the other side.
Possible. Not likely, but possible. So the ACK could have gotten lost. Do you know if an ACK gets lost?
After the timer? After a timer expires?
So expand on that for me real quick. Because I want to know if you know the book answer or if you really know the answer.
I would say the sender would wait for a timeout. He won't know that it's lost, but he will time out eventually, waiting for the ACK. I guess I probably don't know the answer.
No, you're right on. So a naked ACK being just an acknowledgement packet, if it gets lost, nobody in the world will know. No one. Nobody tracks acknowledgement-only packets. If they get lost, it's okay, so long as there's another ACK right by it. Why? ACKs are cumulative. If this ACK goes disappearing into the black hole, and this guy catches up everything up to this point, no one cares about this ACK. Okay? There is no way to detect if an ACK gets lost. No one tracks it. But if this ACK gets lost, and this transfer doesn't happen, depending on the OS, 100 milliseconds, 200 milliseconds, delayed ACK timer goes off, retransmission timers go off, and all these different timers start to go off. Okay, and so people will start to retransmit, they'll start to do TCP keep alives, etc. Okay, but if just a naked ACK gets lost, no one cares because the following ACK is cumulative, and this guy basically says, up to this point, I'm 100% good. We're all caught up. So this actually caught my eye, so we had another high bandwidth conversation. Called the team, said, this initially looks kind of odd, and as I sent out the Outlook notice, I figured it out, right? But I wanted to have the meeting anyway because it's a good learning opportunity for some of the junior members of my team. Why is that? Why did we have data, then ACK? You're almost there. I can kind of see it. No? No? Anybody? Bueller? Anyone? The answer is actually simple. Don't overthink it. LAN environment.
Does the server respond too quick?
Server responded too quick? You're almost there. Look at the timers involved in this ACK. What's the delta between this guy and this guy? 9 microseconds. We're even talking about going down to switch fabric level delay. Okay? So think like a packet. If we rewind the time and you're the server sending this packet out, then this, what was the timing? They're measured in microseconds. So is it possible that these servers came in such a tightly coupled packet train that I meant to acknowledge these two, but another packet came in, interrupt driven, and I acknowledge whatever I had. I'm not going to disregard this guy just because the RFC says every 2 packets. As I'm getting ready to ACK, another packet comes in, and I'll say, I'll ACK that too. Okay? So it's nothing more than it happens so fast that 15 microseconds later, I acknowledge it. That's it. No other reason. Right? The reason why this is interesting is because this data ACK caught my eye. Why did it catch my eye? Because it's unusual. But there's a simple explanation. So I could have gone nuts, but I didn't. I figured it out. But unbeknownst to me, they said, oh, but Hansang, when we use this other NIC, we have all kinds of problems. And it's a next generation network card. So let's take a look at this trace. What do we see here? So do we see similar type of data, etc.? All right. What else do we see?
There's a longer time delay before you start up each send. So send ACK, pause, send ACK, pause,
Yeah.
pause.
Yeah, exactly. So let's take a look at, I got my cheat sheet here, packet number 39 says, for example. Right? So we have a typical behavior where we see data ACK, right? Some delay, keeps going. So let's scroll down a little bit. And what have we here? What's happening here?
Application flow control again.
Application level flow control, we know that because why?
Because you have that push there.
Okay.
Long delay.
And then?
Long delay.
Perfect. That's exactly right. So then the question is, the next obvious question is, why this one, not the other one? It's the same environment. The servers are literally sitting on the same cabinets.
Different drivers.
Different drivers. But, so that's the answer. It's a different driver. So I said, fix your driver. But why? Look at the packet trace and tell me why, and you can figure this out. Why does a newer driver have such a big impact?
Because it generated the ACK for the first 2 packets before that third one snuck in.
Bingo. The fundamental problem here is that you created the evil odd packet by acting too fast. There's a lot of act evil stuff there, so I'll say that one more time. You've created the evil odd packet because you act too fast. In the old trace, we saw data, 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 ACK. Here we see data, data, ACK, data. What happens when you send a single packet? You have to wait. Why do you have to wait? No, that's the rule. TCP says you cannot acknowledge a single packet. You have to wait for 2. That's the rule. I didn't create it. That's the rule. Okay?
200 milliseconds time.
Or somebody gets tired of waiting and says, I was going to ACK you if you sent me another packet, but you didn't. I'm going to sit tight and wait in case you send it to me. Then I'm going to ACK. So a timer goes off, and then I acknowledge you because you sent me an evil odd packet. Odd number of packets, very bad. In this case, my driver's too fast. I didn't wait for this little straggler to come in before I acknowledged it. I acknowledged it up here. Look at the old trace. In the old trace, remember, data, 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 ACK happened after the straggler. So yes, this is an evil odd packet, but it got lost in the wash because the acknowledgement is cumulative. It acknowledged all of these guys. In the new trace, that doesn't happen. It's too fast. It's data, data, ACK, evil odd, delay timer, ACK, and then it continues on. It happens again and again and again.
Okay.
Yes?
So the question in summary, sort of, in my own mind's eye, the application guy is doing these pushes to get his stuff out. And now you're saying we should put a slower driver in, a newer driver's too quick?
Yeah.
So we need to like downgrade to go with the application.
A very cogent observation because my title is... Oh, I changed the title. Damn. Actually, the original title was too much of a good thing. Yeah, it's too fast. Do I have that? Oh, yeah, there you go. See, I must have moved it down here. So here, I'm looking at odd numbers are evil. Really? Always? Not necessarily. I just showed you a case where there was an evil odd packet, but the acknowledgement, being cumulative, covered it. So there's no penalty, right? Not a good practice, but the fact that I got an odd number of packet doesn't hurt me because my ACK was triggered by the first 2. As I'm getting the ACK ready, a third straggler comes in, and I said, I might as well acknowledge that too. In the new driver, the first 2 comes in, I'm Johnny on the spot, I immediately ACK, I see the straggler come in, I already ACKed, so I can't ACK again, and I sit there and wait for the next packet. Okay?
So effectively, the slow driver was masking a potential issue that was there all along.
Yeah.
Yes. So we got the chip engineer on the phone and showed him this trace, and he said, "Oh, you know what? You should change this, and it's called input moderation rate, and it's set to on. You should disable it." And this kind of goes back to back in the days when there was a thing called Ethernet capture effect, and this was a theoretical thing, but it happened. And the Ethernet capture effect says that if you have a very aggressive guy in a shared CSMA CD half duplex Ethernet, if I'm very aggressive, I always win, and I can transmit more than everybody else who backs off. Okay? Not to go off on a tangent, but this was, for a while, everybody went nuts. Like, oh my God, the whole sky's going to fall. Our whole Ethernet's going to fall down. We need to come up with some other mechanism called BLAM, binary backoff. But in the real world, people are like, well, networks are running okay. Do we really need to worry about it? So it was a mathematical, theoretical problem. It could happen. And then some vendors cheated by saying, you know what? After I send a packet, I'm supposed to have a quiescent time, right? In half duplex, it's 9.6 microseconds. Some vendors said, you know what, if I don't wait that quiescent time, I can get a jump on everybody else. Because remember, in shared Ethernet, whoever steps on the wire first wins, right? So if everybody has to sit there and wait 9.6 seconds, but I don't, I'm actually getting a jump on my start line, okay? So it's kind of like sprinters who jump the gun and take the first step before everybody else. You're going to win the race if you get a half, okay? So there was a setting, again, called the input moderation. We disabled it. All the problems went away, okay? This all started because they called me, and it's part of my fault. I taught the server essays about the MSS, the evil out packet, and they did the triaging themselves. And then they came to me and said, look, there's an evil out packet, but there's no penalty. And I said, well, this is the reason why. And we looked at it. And then when they went to the newer one, because I saw that packet ACK, that kind of triggered something in my mind, right? Like, this is unusual. I should file this away. When I saw the second trace, it immediately said, oh, it's too fast, right? So the solution isn't to munge the MSS so that we do the packet buffer so that we always end up in even numbers. It's impossible. I mean, we can't cover every situation where every last application buffer ends on an even number of packets. We could, but it would be a waste of time. There's a better way to handle it, and driver modification was it.
So above all, about the driver and the TCP behavior, is it still a misbehaving application that's doing the artificial flow control?
Yes, it's inefficient, right? So it's not wrong.
Advantage.
Everybody does it. Your job is to try and convince people, let TCP do its job.
Right.
It's guaranteed delivery, right? So that's the book answer. So here's a pop quiz for everybody. Do you really know the answer, or do you know the book answer? Why is TCP called guaranteed delivery?
Because it tells you to fail.
Because it tells you there's a positive acknowledgement for that. Okay, how? How do you guarantee delivery?
You know if it got there because it sends it.
How do you know it got there?
Because it sends an ACK back.
That's right. And how do you facilitate that? How does the TCP stack make sure that happens? What if the packet gets lost?
It keeps a copy of this buffer and waits.
Exactly right. That's where the send window comes in. Okay? TCP can't go back to the application and say, sorry, I lost it. Give me that packet again? It can't do that because you're guaranteeing delivery service, right? It's like a FedEx guy with a signature, right, versus just a mail. UDP is just like a mail. You kind of think it's going to get there, but you have no guarantees. FedEx, on the other hand, will make sure to get a signature, etc. So TCP, in order to do that, has to set aside every packet that it sends into a buffer. And until you positively tell me that you've got it, I can't release those packets into the garbage. Okay? And that's why send window comes in. That's why looking at the receive window is important, because that exposes the send window. And sometimes you might have a send window problem, right? The receiver's saying, hey, I'm good to go. I can take a lot more data, but the sender's not sending. That means that the send window is too small. Okay? So I deliver these 10 packets, and I have to sit here and wait. And you say, I got packets 1 and 2. Okay, packets 1 and 2, you're out of here. I now have room to send 2 more packets. Okay? That's the typical sliding window that you always learn in comp sci classes. Yes?
Now, from yesterday, the send window is decided by what it sees the receive window can do.
Yeah, in almost all operating systems, the default is that the send window is equivalent to the receive window.
Always
And the
slightly
receive
smaller,
window is what you can send.
Always slightly smaller, or exactly
No,
the same?
exactly the same.
Okay.
Yeah. And almost all operating systems give you the ability to tweak receive windows, but not send windows. Okay? But in practice, it's almost always, the send window is always equivalent, almost always equivalent to the receive window, which you can tweak. Okay? Any questions? So the moral of the story here is, not all evil odd packets are evil, or redundant there. Not always, so long as the act happens slow enough that it catches stragglers. Okay? So the goal here, don't have stragglers. If you have a single packet straggling in, delayed act will kick in, guaranteed. Okay, so look for that pattern. Okay. Next question. So I think I'm good on time here. Let me see. Okay, good. So this is a very interesting trace. What is this? Okay, it's another zebra case. So this is actually a little bit off the beaten path. All right, so you got to kind of put your thinking caps on. And I didn't catch this. One of my team members caught this one as we were having the call. So it's kind of a snowy day in New York. Everybody stays home and does Citrix. They call, Citrix is dying left and right. My guy, we got a problem. I said, well, yeah, I mean, it's snow day. It's a capacity issue. You know, don't bother me. And they said, no, it's not a capacity issue. It's something else. Okay, so we joined the call, and we started to troubleshoot. And the first point here is that people are coming in from ISPs, right? Don't treat an ISP traversing application the same way you do an intranet application. Why? No guarantee it's on the internet, right? Even most vendors like AT&T will tell you 3% packet loss is the SLA that they try to live up to. 3% is huge in terms of packet loss, okay? In fact, I could even show you a study where 0.05% causes 50% increase in response time for a financial app, okay? So, and I know that positively because A, I proved it with a packet level study, and 2, I used OpNet simulation to prove it, and we had to upgrade the firewall. But in all honesty, 0.05% packet loss is not on anybody's radar, let me tell you. So the other question is, do you really know TCP? And the reason why I say that is, do you really know TCP, and can you pick out these little things that happen in a packet trace? Okay, and you'll see what I mean when we look at the guy. And did you pick up on why the 500 millisecond delay? Is that sentence? Did you pick up on why this? Okay. And then I got one here: fast retransmit and regular retransmissions. The reason why I put this in here is because I went to a session one time with a vendor, and there was a lady that asked. The guy was talking about something, I don't know, and he said, and this lady raised her question. She said, does this have anything to do with retransmission or fast retransmissions? And the guy said, well, no, not really. And he said, why do you ask? And she said, because those fast retransmissions are killing me. What she meant was, expert analyzer was constantly flagging, fast transmit, fast retransmit, fast retransmit. Is it good? Is it bad? She didn't know what to do. So we'll take a look at that also. Okay, so first, again, spotting something unusual, right? And as we were looking at this trace, one of my guys noticed something. And as we went into a surgical mode where we see something weird happening here, let's everybody look at it, then the real problem came out. Okay? So let's take a look. So we'll do our typical thing. Retransmissions, are these real? Yeah, probably, right? In fact, there are duplicate acts, 1, 2, right? And sometimes we see a triple duplicate as well. What's a triple duplicate? Kind of a oxymoron sounding name. A triple duplicate. What does that mean?
Prompts a fast one.
Yeah, sure.
It triggers a fast retransmit. What does that mean? So that's the exact textbook answer. What does it mean? Walk me through why that happens.
The packet is lost from.
Besides you're answering all my questions. No,
Yes,
I'm joking.
It has to wait, right? If that's the improvement in TCP behavior.
That's exactly right.
If it doesn't,
Yeah.
otherwise it has to wait till the timer goes on.
Right, and Dr. Van Jacobson actually alluded to that, right? Why sit around saying, I don't believe you. I don't believe you. Yeah, okay, I believe you. Let me retransmit. Okay? So a triple duplicate act, right? And it's a very oxymoron naming, you know. Triple duplicate. It means that you sent an acknowledgement. The acknowledgement didn't get to the other guy. Okay? So let's say you're sending me a packet. You send me 2 packets. My act gets lost. Okay? In the wrong scenario. You send me 2 packets, right? And then you send me packet number 1 and 2, and then all of a sudden I see packet number 5. So I know that packet number 3 and 4 went missing somewhere. Okay? So I'm going to send you the acknowledgement for the first 2 that I saw. When you send me packet number 5, I said, nah, I can't do anything with 5. I need 3. You send me some more data, because remember there's some round trip delay here. I get some more data, and then I said, no, I need packet number 3. That's my first duplicate act. I sent the first act. I sent another act saying, no, I need 3. So more data comes in. And I said, damn it, I need number 3. And I send you another ACK. So that's 3 ACKs in a row that I've sent. So that's the triple duplicate ACK. At that time, you as a sender will say, I believe you when you say you lost this packet, so I'm going to immediately retransmit. That's the fast retransmit. In the old days, you didn't believe me, no matter how many ACKs I sent, and you would sit there and wait 200 milliseconds and then say, I haven't heard an ACK, I'm going to retransmit. So instead of retransmitting immediately by believing that I didn't get it, right? Now you do believe me if you see 3 acknowledgments come in a row. That's a triple duplicate, okay? So when you see ACK number 1, ACK number 3, you should immediately see a retransmission. All right, so it's internet application. Am I worried about retransmissions and packet loss? Not really. Do I care? No, not really. Am I going to troubleshoot it? Not really. What can you do, right? It's the internet. Blame Google. No, I'm just kidding.
Are you using a VPN client?
Yeah, it's a VPN client, yeah. So I'm going to actually come over here on one of these packets. They're all the same. I'm just going to this one because it's we've looked at it before. So you can do the typical TCP analysis, but what's unique about this? And as we were looking, one of my guys said, "Oh, this is weird." Right? Packet number 3257. Why is that weird? And 3258. Just start kind of describing it to yourself, what's happening on the screen. These 2 packets, what's happening?
58 seems to be a retransmission of 57. I can't see the sequence numbers.
Okay, so let's check. Is this a real retransmission? Or is this a duplicate packet that got duplicated through a capturing process? How can we check? Well, an easy way is to look at the IP ID. So this first packet has an IP ID of 13,600. That's a stamp that I put on. Okay? You're not required to put it on, by the way. No one says you have to put anything there. You can be 0. You're not breaking any rules if you put 0 there.
Have you ever seen an implementation?
Absolutely. Yeah. And I know that the reason why I said that was because I went on my high horse and said, your application is broken. How can you not stamp? And go back to the RFC, says, it's not required. So this packet is 13,602. So the first one is 13,600 stamp. The next packet is 13,602. Okay? And this is a quick segue into saying that some OSs use every even numbers. So they'll stamp it 2, 4, 6, 8. A lot of them will do 1, 2, 3, 4, 5, 6. Okay? And this goes back to what I said earlier. How can you tell if a server was really busy while you were talking to, and there was some delay in communication? So in other words, you guys are all clients, and I'm the server. You're all talking to me. All of a sudden, from your perspective, you notice that this communication stopped for some reason. Either the communication went down, or I'm really busy. How can you tell? By looking at packet traces.
So the IP ID only increments by 2, and if this OS only does every other one, you've got half a second there where it's not sending any packets.
Yeah, exactly. The IP ID didn't jump by 100, which means I wasn't all that busy, right? If you see a packet from me and the IP ID is 13,000, and the next packet that comes is 70,000, or not, it can't be 70,000, is 14,000. That means in that time, I've sent 500 packets because it increments by 2. Okay, so if the IP ID jumps by 1,000, I've been talking to someone else, and I've sent 500 packets, as a matter of fact. So I'm kind of busy, right? So you know that servers talking to other people, and then most likely it's your problem or a communication problem. It's not a server problem, okay? But yeah, who said that about the, yeah, you did, right? So why is this important? Why is this odd? And this is, again, this is screaming at you saying, look at me. Something is wrong. Why is it wrong? And this is the part about, do you really know TCP?
Retransmission sent without triple duplicate ACK or a 200 millisecond delay.
Yeah. Retransmission rule says a timer has to go off, or you have to have triple duplicate ACKs coming. Do we see any triple duplicate ACKs coming here? No. It could have gotten lost. It's like, it's possible. But at the same time, why 500 milliseconds? As long as I've been doing this, there are no OSs that have a 500 millisecond retransmit timer. They're mostly in the 100 to 200 millisecond range. So immediately we said, this is very, very odd. We need to look at it a little bit more carefully. And what did my guy find? So we do a quick sequence number analysis. Let's do that, right? So let me close the IP editor. Does anybody else think this is fascinating stuff?
Yeah.
No? Okay, because I don't want to be up here just, blowing smoke.
Right.
But it is fascinating. Again, you have to be detective, right? You have to be part detective. You have to be part teacher. You have to be part researcher to get all this, and evangelist and everything else. Okay, so here's 230 bytes. All right, so let's see if we're all caught up. I'm going to rewind and go back a packet or two. And this has this is a pure naked ACK. And my sequence number is 226. Okay? And the next packet starts out with sequence number 226. Are we okay there? We're okay there. Okay? Nothing odd is happening there. I've sent 230 bytes. So if you add the sequence number plus the length, you get the next sequence number of 456, which should be the acknowledgement number from the other guy. Something happens, and I send another 230 bytes. And I know it's a retransmission. Okay? What happened? Oh, wait, who just said that? You noticed that the window size changed, right? So you inadvertently found the problem, but it's not the correct way to find the problem. So the window size jumped because I'm looking at the other guys. So I went from 10, which has 16K, and then 65K. But I'm looking at the other guy's window size. Okay? So we deep dive. Okay? I'm not going to sit here and ask you to see if you can figure it out because it's not fair. Look at the window size here. Okay? So I'm going to bring up my handy-dandy calculator. 65535, enter. 230 bytes minus 65305. So let's recreate this event. He says, I'm all caught up. We're good. Nothing outstanding. Okay, here's 230 bytes. Nothing, nothing, nothing. Okay, here's another 230 bytes of the same packet. And the guy responds with a window size that's less by how many bytes? 230 bytes. So what happened? I'm sorry?
You got the data.
Hmm?
You got the data.
It got the data.
But it didn't process it.
It's still stuck in the stack.
Stuck in the stack. That's exactly right. TCP has buffer, right? We just talked about that, right? Send window, receive window, right? TCP's job is to say, all right, Ethernet driver, you got a frame for me? Give me the frame. I packetize it, depacketize it. Then I give it to the the application itself. And says, here you go. Here's data for you. Okay? And then I do some house cleaning, reset the window size. If I have to acknowledge people, I acknowledge people. But in this case, TCP said, I got it. I know I got it because I'm acknowledging it. But my window size decreased by the exact same amount that it received. So the receive window size goes down by however many data you receive. And you can hold up to 65K or whatever the window size is here. In this case, it's 65K. I can hold up to 65K of data before I give it to the application. I'm not going to do that, but I can. And as I dump my 64K window and shove it up to the application, I'm going to increase my window size and let you know that I can receive more data. But in this case, the TCP stack said, I got the 230 bytes. and then I'm not going to do anything with it. How do I know I didn't do anything with it? Look how much time has elapsed. A second or more is an eternity for network. This stack hung onto this 230 byte packet. I know that for a fact because his window size is 230 bytes less than up here, which was a second and a half ago. And oh, by the way, I sent 230 bytes to this guy. So the sequence of event is this. I send 230 bytes, he gets it, and hangs on to it for some reason. And my window size goes down, as it should. At that point, nothing was wrong. But the fact that a second and a half later, my window size is still the same, down here, means that it got stuck in the TCP/IP stack. Okay? Which means what? Most likely, what happened?
The application's on.
The application died. The application said, I'm out of here, and I'm not going to do any house cleaning. The TCP stack is literally left holding the bag. Okay? So this was a very... question.
I'm sorry, I didn't mean to. In this case, why does it not send back an act? Because that's a second and a half before it sends an act.
So I don't know the answer to that. I don't know why it waited 500 seconds. Maybe the acts got lost. I don't know. So that one I kind of left it as, you know what, I can't know the answer to everything, so move on, right? And I don't know why it did that. But I do know that the application died, didn't send a reset, very nice of them, right? It just died, didn't tell anybody, and TCP said, wait a minute, I got 230 bytes, what do I do with this? I don't know. I'll just keep advertising 230 window size less from my max, okay? And then eventually it resets the connection and things.
This would be a typical representation of an application failure then.
Yeah.
Email server crash, people are trying to connect to
This is actually a crash condition. This is actually what we used to call a bends, right? Abnormal end, right? A bends or a bends, depending on how. So this is where the application completely just loses its mind and can't do anything. And the stack has left with cleaning up the socket with, you know what, I'm done. I'm out of here. And you either do a reset or tear down. Okay? Any questions?
Did they have to tweak the app Citrix to fix it? You know?
I don't know if... so we reported to the Citrix team, and I don't know what happened after that. Okay? But we did get Citrix engineers online.
You said you'd never seen a stack use 500 millisecond timeout, but I guess in this case this one is?
It's not, because I know the window operating, it's XP and Vista on the other end. So I know that timer is not 500 milliseconds. So I don't know why or what happened that caused this 500 millisecond delay to kick in, right? Because I know the sender, in this case.
Could be a difference in stacks between two operating systems. Vista had some new tweaks that came out.
It's actually the sender is, the guy that's waiting is the Windows server, and his delay is absolutely, and at first I thought, did you guys change the delay act? Did you read some white paper and said, oh, I can be more efficient if I delay my act a little bit more? Did you? No, they sent me the registry, they showed it to me, they didn't do that. So I don't know why.
Was it 2008 server?
No, I think it was 2003 or something.
What did you say the customer experience? I mean, it was just slow.
Hung condition.
Hung and
Yeah. The application just stopped responding. Okay? But now I know why. Because the app died, it kept in the stack. Stack did its job, but couldn't move it up to the next application. Okay? So this is proof positive that, again, the network's not the fault. But, okay, recurring theme.
This died on the client side.
This died on the client side, that's correct. And it didn't even just die, it died inside a stack. Okay? Okay, so here, I'm not sure that we would have gotten to that as quickly as we did if we didn't see that mysterious 500 millisecond delay and a retransmission. So I think you pointed it out. It shouldn't happen. You shouldn't wait 500 milliseconds to retransmit anything. There should have been a duplicate ACK, triple duplicate ACK, or a smaller Windows delay before you resend, okay? So that led us to look at it more closely. When we did, and Tom was on my team, said, does anybody think it's odd that 230 bytes, window size is 230 bytes less than what it was? And then someone said, yeah, we just sent 230 bytes. Put two and two together, you know immediately what happened.
This might be a strange question, but if the client was trying to connect to a port that was basically dead at that point to an application, would there be a reset condition?
No, you actually get a port unreachable. Yeah. Okay. So I think from Riverbed, no? Are you from? Yeah, okay. So this is not a bad thing, don't worry. Not a bad thing. Like I mentioned, we have about 230, 250 devices deployed. When our Asia Pacific team upgraded the operating system of the appliance, teller printing stopped working intermittently. And I hate that word, intermittently, because it's very hard to troubleshoot. So we got the, it says sometimes it works, sometimes it doesn't. There's no rhyme or reason. Busy, not busy, I don't know. It's just sometimes when the customer wants to cash out and they have to print a receipt, the receipt doesn't print, they have to reboot, start all over. So we got some packet captures going, and again, it's a transient problem. But what was the time to resolution? 3 days. Once we got the certificate to decode the SSL session. Okay? So not too bad, considering it's a transient problem. Why? Because packets don't lie. Once you have a packet trace, you can almost answer any question there is that needs to be answered. Okay? Because computers are stupid and they always act in a prescribed manner. Okay? And as soon as you see it going off that beaten path, warning bell should go off. All right? So the right point, am I capturing in the right point? Is it worth? So what does this all mean? It means that in WAN acceleration, there are different ways to do this, but, and this is an old diagram, you can tell it's 7206s and 2651s, 2950s, but here's a PC, goes to a switch, hits the branch side WAN optimization box, okay? And that's where the TCP terminates. It proxies TCP connection, okay? So as far as this guy is concerned, he's really talking to here. That's it. This guy then sends out a packet here, and they negotiate, and they realize they're WAN optimization guys, and it opens up a new TCP connection. This part I said is obfuscated here because this is where the magic happens. Okay? Your IPs are not seen here, although you can configure it that way. So this is where all the TCP stuff happens that normally you can't make heads or tails out of. Symbols are being sent across, control traffic, etc. Then this guy pops out a packet to the server on behalf of the PC. So if you're capturing here, your source destination IP is exactly the same as here. But the sequence numbers won't match. Okay? Because this is a whole new TCP segment. So to catch this problem, where should you deploy your probes or capture points? Can you do it just from here?
From both ends, right? On both ends.
Yeah, exactly. So because these are Linux-based, they have TCP dump. So we dumped TCP from here and here to see what happened. Okay? So once we did that, this is the result. So client side. So I'm going to do my thing, right? I'm going to do what? TCP. Mm-hmm. You should just do this. Automatic. Okay? Nothing. So pretty clean, I think. I'm sorry?
You should have a button too. Because you're typing out TCP analysis line.
Sure. It's a quick segue. For some reason, I can't type BGP. I always type BPG. I don't know why. I do. So show IP BGP sum is a key command that you always type. So when I was taking my lab, you're under tremendous time pressure, right? You got 2 days. It's a 2-day lab, and every time you mistype a command, the router sits there and says, "Let me try to name resolution for you," and you waste time doing that. And I got so freaked out before I went to the lab that I wrote a macro on routers. You can do that. You can actually type aliases, and I did show I, right? And I don't know why I put SI foot, but show I was show IP BGP sum, and because in my mind I couldn't afford the few seconds the CLI sat there thinking, I don't know this command. Let me wait. Okay, please type it again. So here, if you notice, I never really successfully typed show up TCP analysis flag correctly the first time. I don't know why I always mess it up, but I have anyway. So just I kind of went back to flashback, being nervous and I gotta get this config down. All right, so let's take a look at the client-side trace. Oh, this is the other one. I closed it, so let's open up the client.
Do all Riverbed devices have Linux? Is that there?
Yeah. So even though I actually had a SSH key, I brought it with me, but as Saki pointed out, I didn't. This is a SSL reuse, so I didn't capture the initial handshaking, so I can't decrypt it for you. I can show it to you a little bit later because I have another tool that caught it, but it's actually not important. So if we look at this trace, it's doing something, and it sent about 25K of data. Turns out to be a post. He was doing a post. And it sent about 25K of data because, again, my delta and time and my cumulative bytes are all standard in my Wireshark. So I know that my post took about 25K worth of data. So I extracted this exact same conversation on the server side. Okay, and again, even though I manually munched the IP addresses, you have to believe me that it was the same conversation. And yeah, there's some packet loss. Okay, nothing to worry about though. But I'm scrolling down here and thinking, whoa, wait a minute. 1,300 packets? How many did the client have? 62. So my immediate reaction was, what the hell? WAN optimization is supposed to reduce packets in bandwidth, not explode it from 60 to 1,000. So what's going on here? I'm doing a post. It's a typical HTTP. How can you improve HTTP-like performance?
Prefetch.
Yeah, you prefetch. You say, you know what? I saw Joe Bag of Donuts over here. He went to this URL, and he brought down all these images. So the next time someone goes to that URL, let me go get it ahead of time. Okay? So it's a typical, caching. A lot of browsers do this on their own. So we went from 62 to how many packets? 103, right? 100K, right? So we said, oh, this is interesting. But we said, oh, yeah, but it prefetches. It shouldn't break anything. It's just prefetching stuff. So why is it breaking? So when we decrypted this with Wireshark, I can't do it here for you, but I actually have another program that I use called IE Inspector. Let me bring it up.
Is that free?
Hmm?
Is that free?
No, this one is not free actually, but it's very cheap at the same time. So it hooks into IE process, or you can use it as standalone, and you can capture. This is a browser sniffer, so it doesn't matter if it's encrypted or not. Because it hooks in before the SSL encryption kicks in. So immediately we said, all right, these are all the prefetches that's happening. Okay? So that's understandable. But why is it dying? That's the question. We understand about prefetching, but why is it dying? So we got Riverbed folks engaged, and we started looking at it. And there's a setting that I didn't know. Right? I saw it a million times, but I never knew what it meant. There it is, right here. Apache has 2 keep alive timers. I knew about the first one, never even knew about the second one. Does anybody know what the keep alive is meant to do in HTTP 1.1? I actually should bring some of those traces, maybe next year. HTTP 1.0 was stupid in that it opened up a TCP connection for every object. So if the web page had 10 pictures, I would open up 10 TCP connections to fetch those objects. And we all know that's bad because of slow start and handshake round trip times, right? HTTP 1.1 said, that's kind of stupid. Let's open up 2 by default and pipeline data through them so I don't have to experience slow start. And keep alive is one way of doing it by saying, hey, I'm HTTP 1.1 and I want to do keep alive, right? You tell the server, I'm capable of doing keep alive, let's do keep alive. And the server says, I'm capable of doing keep alive, let's do keep alive. So what does this timeout mean? Does anybody know?
If it's idle for 10 seconds, kill it?
Yeah. If it's idle for 10 seconds, I don't trust you anymore. You're going to have to renegotiate with me. Okay? So I knew about that. And I said, boy, this 10 seconds is really dumb. Right? Turns out, that was a blessing in disguise. So this means that if a teller stops and says hello to you, and that takes more than 10 seconds, his or her connection just died and has to be respawned. Not died in a bad sense. the application just closes out the connection and opens up a new one. Okay? As long as you're clicking around for 10 seconds, within the 10 second, the idle timer resets. Okay? So, like in BGP or OSPF, this is a dead timer. Okay? As long as you do something within this timer, as it counts down from 10, 9, 8, 7, and you click on something, resets to 10. And counts down and resets to 10. So I knew about that, and the first thing I said was, that's really stupid, 10 seconds, come on. You know, like I said, if you say, hey, how you doing, how's your son, that's 10 seconds. But then I didn't even see this. All these years of doing these analysis, I never paid attention to that. And Riverbed Engineer said, this is your problem, right? What does this max equals 100 mean? Well, these guys are from Google. I Googled it. And it says maximum number of objects that can be fetched. Defaults to 100. Again, defaults are the guardian angels for the clueless, right? This is to prevent someone from downloading continuously in one connection without re-authenticating. So after you've fetched the 100th object, Apache Web Server says, that's enough for you, I'm going to give somebody else some chance to fetch these objects from me. And it closes that connection out. Okay? So when I was doing the post on the client side, I only had about 20K worth of traffic, right? Not that much data. On the server side, what was the WAN optimization guy doing? Prefetching. Prefetching a lot. And it's a boundary race condition. If in that 10 seconds I've reached the timer, I close out the connection. Right? Because that's what HTTP rule says. I've reached my token of 100, I need to close this connection down. And oh, by the way, so he did one operation, he does 100 in 10 seconds, and this web server up here says, we need to close this connection. And then he says, we need to close this connection. We need to close this connection. Only problem is, this is Internet Explorer 6. IE6 is very stupid when it comes to handling SSL type transactions. Okay? It's not just a bashing on Microsoft just because I want to bash Microsoft. That's not it. Error handling of SSL pages in IE6 is lacking. Okay? So you will see times when you see page cannot be displayed. Right? And some of you may have experienced this. And it happens because it, the way it tears down SSL connections, the way it handles keep alive, it's very poor in that respect. So if you happen to be in a race condition where within a 10-second window, you've fetched 100 objects and you try to close it out gracefully, the PC isn't so grace. So the printing fails. But if I had enough tokens, so in other words, if I was at like object number 30 when I did this, I'm screwed. Because I'm going to go fetch about 80, I'm over my 100, I'm going to close my, okay? But if I happen to be at counter 99, I don't fail. Because I've prefetched about 80, I still have 20 more to go, I've done my printing, and then I gracefully close and respawn another session, okay? So when we look at the packet trace and notice that big explosion, and we got Riverbed engineers on the line, the first thing they said was, that's weird. Time's up. Are they kicking me out?
Is that your timer? Is that your...
You got a flashing light.
You got a failure up here.
Oh, that's the last one. Okay. So what happened was when that happened, it was a race condition, and what was our solution? We asked the developers to say, you know what, even the Apache man page says set it to 500. Because in an intranet application, is there really a lot of danger of people monopolizing a connection and fetching a lot of data? Good for them. They're supposed to fetch a lot of, that means they're working hard, right? So we had said, set it to 500 like the man page says, right? Recommended value 500. The other thing was we told the WAN optimization, stop prefetching. Okay, so we dumbed it down so that the max count, the counter of 100 doesn't get triggered. Okay? Any questions? Okay, That's perfect. I know we have to skip a couple, and I kind of blew by this. So what I'm going to do is when I post these transactions on the web, or the PowerPoints, the detailed answers to all the questions that I ask will be included in an answer sheet. Okay, so you don't have to like go back and say, what the hell was he talking about here? Because my PowerPoints, they're not verbatim. In other words, I don't sit here and read the PowerPoints verbatim line, but you can do that on your own time. And at the same time, I don't give you the answer. So if you look at a week from now, you're kind of like, what the hell did he say? Yes.
I'm not sure who asked about it, my inspector, but Fiddler 2.com
Yes.
is free.
Yes. So Fiddler is another tool that you can download. And why do we use IE Inspector? It's graphical. It produces nice reports. You can export it XML. You can export it as a spreadsheet. And it's pretty cheap. $3,000 for enterprise license. Can't go wrong. Okay. Any other questions? Anything about what we covered? The key points, though, is you really have to know the protocol to be able to spot these weird things that happen. Okay. It doesn't just happen to me or my network. It happens all the time. It's just up to you to recognize them. Okay. So a lot of these are like little blips that you may or may not catch, but if you're attentive and you know the protocol, you can spot all these weird things happening and then say, this is weird, I need to investigate it. At the same time, know the environment so that you don't go off ruling out things you don't need to rule out. In a LAN environment, very little delay, you don't need to worry about window sizes for the most part. Even an 8K window size is fine. Why? Because I can never exhaust my window size. By the time I send a packet and I get an ACK back, I'm okay. All right? Learn to recognize different symptoms. How long does it take a full-size Ethernet packet to traverse a T1? You should know that immediately. Yeah, about 8 milliseconds, right? It's simple math. How many bits per second? How many bits in a packet? 8 milliseconds is what it comes out to. So if you see a consistent 8 millisecond latency, you can say, oh, are you on a T1 branch? Okay? These are things that you should know how to do subconsciously so that you can, because if you do, eventually it's osmosis. The more you do this, the more you start to pick up on these little odd things. Okay? And these are like signposts that tells you which way you should go in terms of troubleshooting. All right? Okay, that's it. Thank you very much. And,